In previous videos, I had showed that the slope of an object's position versus time graph is the velocity of that object. And this means the velocity is the derivative of the position versus time graph. What we'd like to do here is use antiderivatives to start from a velocity versus time graph and find out what the position versus time graph of that object would look like. Below I have the velocities of two objects, and they're just constant velocities of -2 meters per second. And some information about the object's locations is given. So from this information, we ought to be able to draw the position versus time graphs of each of these objects. I'll start by just giving a formula for the velocity. It's a constant -2. Now sometimes with velocities, we like to put subscripts to notate them. And the x here just means that this is a velocity with respect to the x direction. The reason it's used is because we can also have two-dimensional and three-dimensional motion too. And so we could have velocity in the x, y, and z direction. Some textbooks will just leave it off and just assume it's implied here that we're dealing with the x direction. Anyway, let's go ahead and integrate the velocity function, because that is how we'll discover what the position versus time function looks like. The parentheses with the t here doesn't mean multiplication, it's just function notation, which means that time is the input to the velocity function. So you could have it, or you could actually leave it off, and either one of these is acceptable. But let's plug in the function that we have here. And that's what we want to find an antiderivative of. This time our horizontal axis is time, t, so our differential references that. It's dt instead of dx. And so when we do find that antiderivative, we want to attach the -2 to a t instead of an x. Now, as we've seen in the past, indefinite integrals should always be attached with a constant plus c of some kind. In the context of position versus time graphs, though, we like to give that c a name that's applicable to its meaning. C is an initial value of our graph, and for that reason, we can use the letters xi perhaps, or xo. So I stands for just initial, the initial position of the object, whereas O is said x naught, and it just means the same thing. Some textbooks use xi, some use xo. Either one is acceptable. And now let's go ahead and set that function equal to our position. That's great. And our last step with this is going to be to use some information given in order to, if we can, find out what that xi initial position actually is for this object. Now they say here that at time 0, the object is located at x of 0 equals 4 meters. So that's a point we can actually plot on our graph right now. It's right here. That is the xi or xo. Okay, and so that's going to be the answer to what is the xi. We have to replace it with a 4. And this is the function we're looking for. Now we're allowed to leave the units off of formulas like this in mathematics. That's kind of common. But we should always assume that the units are there. Okay, so x is a function that's given in meters in this case. Now let's try to sketch it. And notice that our derivative function does go to the left, and it keeps going forever. So we want our position function to do the same. And we just need a nice straight line between all those points. All right, and the problem's done. Now, just to see how this compares to an object that may have a different starting position, let's do the same process for the problem here on the right. Obviously, our function is going to be the same for the derivative. It's just a constant -2. We want to build up to the antiderivative. We're going to get -2t plus xo. And that's our function. They give us one point that the graph of our position has to touch. It says that at time t equals 5, our object is located at x of 5 equals 0 meters. So that's going to be this point here. Okay. That is the point 5, 0. And now we just want to use algebra to find out where this graph touches the vertical axis. So to do that, start with the function. And we've got 3 important variables here. And we just want to plug in this point. So let our x of t be 0. And let our time be 5. It's a really easy algebra technique. And all we're doing here is just plugging in a 0 for the vertical value and a 5 here for the horizontal value. And now we have one unknown, the initial position, which we could solve for. All right, I get 10 as our vertical intercept. Now we can plot that point. And we could go on to sketch the graph of this object. As we can see, it's a little bit different position versus time graph than the previous one. The previous one had intercepted the vertical axis at a value of 4. Whereas this one intercepts at a value of 10. And that's all based on information that was given to us in the problem. They do have the same slopes, so they have the same velocities, but they have different starting points. Now we can finally erase that xo and plug in the actual initial value, which was 10. And this will be our final answer for the second one.